got the impression that some of the stuff I've been talking about at the end of last time must have been pretty confusing, especially these line bundles on elliptic curves. So I want to say a little bit more about that to maybe try and clarify that, but not right now, maybe at the end of this lecture. So, I want to switch to something else and tell you what it means for a line bundle to be positive or of positive curvature, which is a condition in Kodaira's embedding theorem. So that's, I think, maybe more important and also easier to understand than this stuff I was talking about at the end of last time. So positive and negative curvature. So there are two things I want to do. So first off, there's a formal part where I'm sort of going to define what means for. So curvature is a property of a metric, and the metrics that we're going to be considering are metrics on line bundles, so fiber metrics on line bundles. We have a metric on every fiber. There's connections in the game also, connections on line bundles, but I'm not really going to be mentioning those very much. And a connection has curvature. So on line bundles, and I'm also going to be mentioning Chern classes briefly. So once you know what curvature is, you can define Chern class of a line bundle. So it's a characteristic class. This is the simplest example of a characteristic class of a vector bundle. And then I want to discuss a little bit what it means for a line bundle to be positively curved, so geometric meaning. Of positive and negative curvature. It's sort of going to be a toy version of the discussions that you usually do in Riemannian geometry, what it means for a manifold to be positively or negatively curved. It's sort of like a baby version. The curvature only comes from these line bundle directions in a sense. It doesn't exist on the whole manifold, but there's some nice geometric features that you can talk about nevertheless. Okay. So for manifold or line bundle, and so first thing I want to say, what do we mean by metric on this line bundle? Hermitian metric, to be precise. So a Hermitian metric on L. So it's kind of the usual thing, right? When you want to say that there's a Hermitian inner product on each fiber of your vector bundle, and that sort of varies continuously or smoothly as the fiber varies over the base. But sort of partly because complex line bundles are so easy, so there's only one complex fiber direction, a Hermitian metric on a fiber is just a real number, really. I mean, it's basically given by one real number. So Hermitian metric is really basically just a function, essentially. So it's more convenient to actually define it in this way. So that's as a function on the total space of the line bundle. From the total space to R, such that H is non-negative. That's a metric property, and it's, I think of H as the norm squared along the fibers, like the radius squared along the fibers. So it's homogeneous of degree 2. If I scale by a complex number, if I scale my vector by a complex number, then sort of the modulus squared of the complex number pulls out. So H of lambda V is supposed to be lambda squared, mod lambda squared H of V for all V in the line bundle for all complex numbers lambda. And once you have a Hermitian metric like this, it makes sense to talk about sort of the unit sphere bundle of the Hermitian metric, or the unit ball bundle, really the unit circle bundle and the unit disk bundle. So if you're looking at all vectors in the line bundle where the norm is precisely equal to 1 or lesser or equal than 1. So if it's lesser or equal than 1, you get this kind of tubular neighborhood of the zero section, and then that gets a special name. So it's called the Grauer tube of the metric. This is T sub H. So then I'm going to define the curvature for Hermitian metric, and there's something that needs to be proved here. Sort of, if I stay away from the zero section of my line bundle, then the following is true. So you can take minus IDD bar. So the minus is conventional, but it's there to make sure that positive curvature really, corresponds to positive curvature in all cases where we already more or less mean or more or less know what that's supposed to mean. So that's why the minus sign is there. So away from the zero section, next the Hermitian metric, I don't want it to be identically zero. Away from the zero section, then the metric is actually strictly positive, so it makes sense to take log of H and take del L bar of that. So it's going to be a 1-1 form on the total space of the line bundle defined away from the zero section. And I'm claiming that that has a particular property. I'm claiming that that's actually pulled, it's defined as a 1-1 form on the total space, but I'm claiming that's actually pulled back from the base of the manifold. So it comes from something downstairs. So it's actually P star of omega H. So P is the bundle projection. For some 1-1 form, omega H on the base on M. So the interesting thing about this one form is that it's, omega H, the one that lives on M, is going to be closed but not necessarily exact. Whereas, this I del L bar thing up here that lives on the total space, that's sort of exact by definition. So then omega H, that's a curvature form. third statement is that curvature form actually defines an invariant of the line bundle, topological invariant of the line bundle, independent of what Hermitian metric I used to define it. So the class 1 over 2 pi times the curvature form, claiming that as a class in the Ram cohomology, is independent of the choice of H. It's called the first Chern class of the bundle. So there's no second Chern class for line bundles anyway. You can define Chern classes for complex vector bundles of higher rank, and then there's going to be higher Chern classes as well. But for line bundles, it stops there. So there's a couple things that need to be proved. So this claim in 2 that this curvature form actually is something that comes from the base. And for that we can work locally. So we fix a local trivialization of the line bundle. So that's going to be isomorphism to trivial line bundle over some chart. And if I pull back the Hermitian metric under this isomorphism, then I'm claiming that there's a very simple way of actually writing it in these local coordinates, sort of under F. It's going to be true that H is just e to the minus phi times mod z squared. So z is the coordinate along the fibers here. Another point, what is locally mod z squared is a Hermitian metric on this line bundle in the sense of that definition, because it's non-negative, it's not identically 0, and it's homogeneous of degree 2. So it's clear that if I take, so mod z squared is a Hermitian metric locally, H is a Hermitian metric by assumption, so the ratio of the two is homogeneous of degree 0, because sort of both sides scale in the same way if I multiply by lambda. And because lambda is a complex number, so there's r and theta, so this means that this function phi here is actually, invariant under, it's constant in the r and in the theta directions. So phi actually has to come from the base. That's the point. So by homogeneity, and notice that phi depends on f. So if this trivialization f, there's different possible choices. So what this fiber coordinate z means relative to the original line bundle actually depends on the choice of trivialization f. And so therefore, if I don't like the phi that I got for some particular reason with one particular trivialization, then I can try and change the trivialization to get a better phi. So it's like choosing normal coordinates in Riemannian geometry, more or less. So that way I can sort of achieve that the differential of phi is 0 at a given point, sort of corresponding to the fact that the Christoffel symbols of a Riemannian metric can be made to vanish by picking normal coordinates for the metric, that sort of thing. So you're going to be working with phi, but you have some freedom in what phi actually is. But then it's kind of clear so long as you stay away from the zero section, then minus IDD bar log h. So if the log mod z squared goes away, and that's, it's log zz bar. So it's log z plus log z bar, and the del kills one of them, and the del bar kills the other one. So as long as I stay away from the zero section, where sort of del bar of this guy gives me like a delta function component, then this doesn't actually contribute. So all that's left is IDD bar phi. And that lives on the base. Okay, so that's that. There's a couple things that need to be proved here. So, that the curvature form is closed, so that it actually represents a class in the RAM cohomology, is clear from the same representation. Closedness is a local property, and locally I can just write it as del bar of a function. So if I apply d to it, then I actually get 0. So it's definitely closed. Yeah, sure.
You get rid of exponent and you get phi just?
How do I get rid of? Yeah. So I'm saying the. No, say it again.
So there is exponent here, but there is no exponent there.
Log.
Yeah, log.
Uh-huh. I mean, I know that the ratio of the two guys is going to be a positive function, so I can write it as e to the minus phi.
And where is it? Is it square?
But that's holomorphic. See, I mean, locally, I've identified the thing with a product domain. U is a domain in Cn, and now I've taken a product with C. Okay? So dd bar log z squared is actually 0.
Right. But
Yeah?
When you take log of exponent, you still have to multiply by z squared.
So take log of e to the minus phi mod z squared. That's, yeah, you don't have to. So the first thing here is that the first implicit claim is that this is actually a real cohomology class. I mean, this is never completely obvious in this business, because you have del and del bar floating around. The definition of del and del bar is strictly complex, and I put the I in front. I mean, the I in front is exactly what ensures that the thing is going to be real. So that's the first thing. So why H2MR and not MC. So we're going to take the conjugate. I mean, all we need to do is check that, if we take the complex conjugate, that's actually the same thing. So of this guy actually. So I dd bar phi bar. Well, so it's going to be minus I d bar d phi bar, but phi is a real function, and dd bar anti-commute. So I actually get I dd bar phi. So it's actually a real valued form. It's a two form, and if I express it with respect to real coordinates, then the coefficients are going to be real as well. So the second point is why is it actually independent of this choice of Hermitian metric? So I can do a similar argument as here. I can say if I have two Hermitian metrics, then both of them scale in the same way along the fibers. So the ratio of the two is scale invariant along fibers, both in the r and the theta directions. So the ratio between the two Hermitian metrics has to come from the base of the manifold. It has to be a function on the base of the manifold. Positive function because neither of them are identically zero. So given h and h tilde, can write h tilde as e to the minus psi h, where psi is a real valued function on the manifold, and then sort of omega h tilde is going to be omega h plus idd bar psi. So the form changes by del bar of some scalar valued function, and that's exact, right? I mean, you could write this as omega h plus, I don't know, you could write this as d of I del bar psi. Except that doesn't really help so much a priori because this is a complex form. Again, and you want to write the difference as d of a real form, but this guy is real, that guy is real, so it's kind of clear that all you have to do is symmetrize here with respect to complex conjugation to get something real. So what you really want is 1/2 of d bar, I times and then this guy here is actually real. So you can check that it's equal to its complex conjugate pretty much obviously because you get the minus sign from the I and then the del and the del bar switch. So it's actually, this is a real 1-1 form if psi is real, which it is in our case. So sometimes people, whenever you actually have to worry about forms being complex or real valued, then it's so slightly more convenient to, not to use del and del bar, but to equivalent operators. So you have del and del bar, you have d is real, del and del bar are not, and this guy is real again. So it's better to, instead of del and del bar, to use d and this guy, so that gets its own name. So write dc psi. So this is I times del bar minus del psi. So that's a real operator, preserves reality of the form.
I guess you just need one more.
Yeah, thank you. Yeah, exactly. Yeah. So that tells you that if you change Hermitian metrics, then the cohomology class of the curvature form stays the same. So it's actually topological invariant of the bundle and not of the Hermitian metric that you chose. It's easy to see that all bundles do have Hermitian metrics because locally it's clear, and then you just glue them together with a partition of unity because a convex combination of norm functions is a norm function again. Just write that down as a remark where it said that. So omega h is sort of IDD bar exact locally. But not usually globally. Um, but so by contrast, this, I mean, P star, if I pull it back under the bundle projection, so from the base to the total space and then restrict it to the complement of the zero section, actually becomes IDD bar exact globally. So that's, so again, if you're so familiar with characteristic classes and vector bundles, that's a typical phenomenon. I guess it's called transgression. If you have a characteristic class of a vector bundle and pull it back to the, to the unit sphere bundle of the vector bundle, or at least to the total space minus the zero section, actually becomes exact there. This is how you prove the Gauss-Bonnet-Chern theorem in general using this trick. Also say that again, so it's a topological invariant of your bundle, really. So it's not surprising that there's actually purely topological construction of the Chern class that doesn't use this sort of crutch of Hermitian metrics. In particular, the Chern class is an integral class, really, if you go into the topology. I mean, we're not going to need that. I'm just going to say that. So in fact, and this is sort of what explains this funny factor 1 over 2 pi that wouldn't make any sense otherwise. So because of the normalization 1 over 2 pi, it's true that the first Chern class lies in the image of the map from integral to real cohomology. So the avatar of an integral class that could be defined purely in terms of topology. So from that point of view, if you already know what integral Chern classes of vector bundles are, then this is sort of the simplest example of a statement in Chern-Weil theory that relates characteristic classes to curvature expressions, or polynomials in the curvature of connections on your vector bundle. But what's going to be important for us next week is that these Chern classes are actually computable, either from topology or sort of straight from the definition, because you can verify that the Chern classes that are defined in this way, without talking about topology, actually verify all the same axioms and sort of basic, cut and paste properties that the Chern classes from topology do. So it can use sort of the same computational procedures as in topology to, compute these guys, which you're going to have to do at some point. Okay, so one more remark. Why do we call this thing a curvature form in the first place? And so for that, it's probably best to think about the case of Riemann surfaces. So we want to make contact with Riemannian geometry. So understand curvature of Riemannian metrics perfectly well. We have an intuition for what it means for the metric to be positively or negatively curved. So what's sort of the one case where we can make contact with that intuition? It's when the tangent bundle of our manifold is actually a complex line bundle. So then sort of these Hermitian metrics and Riemannian metrics are pretty much the same thing. And that's the case of Riemann surfaces. So if you take M to be a Riemann surface, and L the tangent bundle of M as a holomorphic line bundle, well, if you have a Riemann surface, it means you have a topological surface or a smooth surface, but you're also fixing a conformal class on the Riemann surface. So an arbitrary Riemannian metric is not going to be good enough for us. I mean, it has to respect the conformal class, so it has to induce the same structure of angles that's already given to us by the complex structure. So we're going to say that H. I mean, have to take H to be a conformal Riemannian metric. Metric on M, and then that's exactly the same thing as a Hermitian metric on Tm viewed as a complex line bundle, as a holomorphic line bundle, and e to the minus phi is just a conformal factor. The metric is local. You pick holomorphic coordinates for your metric, dz bar, and then the conformal factor is e to the minus phi. So it sort of translates verbatim to the setting sort of conform. I mean, it's exactly the same formalism as when we're talking about conformal Riemannian metrics on a Riemann surface, and then it's kind of the formulas for the curvature are the same. So then it's actually going to be true that omega sub h is basically just the Gauss curvature of this metric. So they're not even any factors here. So most importantly, the sign is the same, but there's not even the 1/2 as far as I know. So it's it's the Gauss curvature. So it's a scalar quantity times the area of form. And notice that that's a scale invariant quantity, because if I scale my metric up, then the area of form goes up, but the Gauss curvature goes down at the same rate, so the product stays invariant. So it's a scale invariant quantity. And it's kind of clear because scaling means that I multiply e to the minus phi by some number, meaning I change phi by an additive constant, and so then if I take del bar, the additive constant goes away. That's a scale invariant object. So there's things you can do. So the main example is the tautological line bundle OPN of -1. And there's no perfectly canonical Hermitian metric on that line bundle. So a fiber of that line bundle is just a straight line, complex line through the origin Cn plus 1. And now I need a way of measuring lengths in that fiber. That's what a metric is. Well, there's a perfectly canonical way. If my fiber is just a straight line in Cn plus 1, I have the Euclidean metric on Cn plus 1, and I can use that to measure the length of a vector in the fiber. I can just put h of v equal to mod v squared. So v is in L, and this is of the Euclidean in Cn plus 1. So it's the most canonical thing I can do there. And then we can try and compute the curvature of this thing. So, so I take my affine charts in projective space. So on U sub I, my standard affine chart. So remember I mean, my canonical local trivialization for O of minus 1 is to take, affine coordinates on that chart. So this is just little z naught by little zi and so on. So these are affine coordinates. And then little z, so that's my fiber coordinate. And then I just map that to z times the vector z naught. And then in the ith place, I put a 1 onto Cn in Cn plus 1. So that's my canonical trivialization. And z is this holomorphic fiber coordinate that doesn't really play a role if I compute the curvature. So really, I have to take the Euclidean norm squared of this vector, but the mod z squared goes away if I take the del bar log. So what's left is what this stuff is telling me. Is that omega h is actually equal to minus IDD bar log plus mod Cn squared. I'm just putting plus 1 in the ith component. So I actually want to compute this in the case of the projective line. So I want to compute this form explicitly and see what it looks like. So when n is equal to 1. So I'm just working on C. So maybe I shouldn't be calling it C. With coordinate W, and so I care about the form omega h, so that's minus IDD bar log mod W squared plus 1. That's minus I del 1 over W squared plus 1. Then I have to take del bar of the inner function, so that's W dW bar. It's going to have two terms now, minus I. So there's a 1 over mod W squared plus 1 dW wedge dW bar minus W over W squared plus 1 squared. And then del of this guy, so that's just W bar dW wedge dW bar. So that's a mod W squared. Squared here. So raise the power, get the W squared plus 1 minus W squared. So that's actually just minus I times 1 over W squared plus 1 squared times dW wedge W bar. So let's maybe rewrite this in terms of real coordinates to get a better impression of what's actually going on. So if I write W as x plus iy, then dW wedge dW bar is minus 2i times dx wedge dy. So I have a minus I times a minus 2i So that's minus 2. Okay, so minus 2. That's what I don't want. So that's negative curvature. So the x wedge dy is the area form of CP1 with respect to the preferred orientation. This is x first, y second. So it's of the preferred orientation of the complex plane. And now I'm multiplying by a negative function. So it's like having a Riemann surface of negative Gauss curvature, except that O of minus 1 is not the tangent bundle of CP1. But so that's negatively curved. So that's a definition you can make in general. So if you want to say what it means for a line bundle to be negatively curved, is that you take the curvature form and you restrict it to every possible complex line in the tangent space, and then you want to get something that's, if the line bundle is supposed to be positive, then you want that to, it's a 2 form on a complex line, so you want that to agree with the standard, complex orientation of your complex line. So that's one quick way of saying what it means for a bundle to be positive. Positively curved. If for all points P and M, and for all complex lines in the tangent space. Sort of omega h restricted to that complex line. It's a positive multiple of the preferred orientation. Of complex orientation on L. And then one thing that's pretty easy to see is that there's one canonical way of reversing the sign of the curvature of a line bundle, and it's just passing to the dual. Or more generally, if you pass to a tensor power, then you can either, yeah. Sorry, say that again. No, a complex. I mean, the curvature form is a form on the base. So I want to restrict it to complex lines as of tangent to the base, or if you want like holomorphic curves in the base. Yeah, sorry. So one healthy computation you can do is, to verify that this stuff that we're saying about topology and integral definitions of the Chern classes actually makes sense. So what you can do is you can actually take the Chern form or Chern class. So that's 1 over 2 pi times the curvature form. So you can just integrate that over C. And that's a pretty easy integral in polar coordinates. It's pretty straightforward. You can calculate that that's actually equal to 1, as it would have to be. So I'm pairing this class with the fundamental cycle of my manifold. If it's an integral class, then the result should be an integer. And it's -1. So I'm taking the negative guy. So this means that So this means that the first Chern class of OP, only checked it for P1, but it's actually true for Pn. This is minus. So the preferred generator of the second cohomology of projective space. It's integral, and it takes the smallest integral value that it possibly could. So the class actually generates the cohomology of projective space. And so if by passing to the tensor powers from O of -1 to O of k, meaning that I can realize every cohomology class in projective space as a Chern class of a line bundle of some O of k. And that's sort of pretty suggestive. So what that suggests is that that sort of points towards a way of proving that the O of k are actually the only holomorphic line bundles of projective space, because their Chern classes sort of exhaust all the possible cohomology classes of projective space uniquely. Suggests a proof that for the only line bundles. But sort of what we're left with checking is whether the Chern class actually determines a line bundle uniquely, and that's completely false in general. So for example, in elliptic curves, it's completely false. So when does C1 determine L up to isomorphism? Well, so I can't really prove this here, but I can there's many possible proofs. I can sort of give you the idea and tell you what steps are needed. Some pretty standard steps. So if C1 of L is equal to C1 of L tilde for two line bundles, then this means that, I can take a quotient of two line bundles. I can take L1 tensor, the dual of L tilde, so that's a trivial class. It's a trivial class. And now you need a result to go from curvature forms to metrics. So you want to know that that means that there actually exists a Hermitian metric of zero curvature on your line bundle. And that's not trivial. So if M is a Kähler manifold, and I'm maybe going to explain that on Monday. So if M is compact Kähler, then you can use the Del-Del-Bar lemma to show that this means that there exists a Hermitian metric of zero curvature. On this guy. Now you need one more ingredient that I sort of swept under the rug, which is that you have metrics and curvature. So there's connections in between. Didn't really want to introduce connections here because we're not going to need them really, but you can define sort of a connection as an intermediate concept so that the curvature form of the Hermitian metric is really the curvature of that connection on the line bundle. So this means you have a flat connection, a connection with zero curvature. So this means that parallel transport along paths in the space only depends on the homotopy class of the path. So if your manifold is simply connected, which elliptic curves are not, but projective spaces are, then you can actually use parallel transport to trivialize a line bundle globally and actually holomorphically. So parallel transport with respect to that connection is a holomorphic thing. There's a complex linear thing, so you can so if the manifold is simply connected, to trivialize this guy holomorphically. So in a compact Kähler manifold, which is simply connected, it's actually true that the Chern class determines the line bundle. So in particular in projective space. So modulo the Del-Bar lemma and this business of there being a connection in between the metric and the curvature, there's actually sort of pretty clear-cut result. If you care, I have a sheaf theoretic version of the same argument that still uses that the manifold is scalar. So if you want to know about that, you can ask me. So, yeah. That's that. So that's one possible path that you could branch off of, based on this computation. Classification of line bundles. So another thing that's suggested by Starr is a result that I'm just going to state. Suggested by Starr. So the first Chern class of O of plus 1 of projective space is sort of the positive generator of the cohomology. Now O of plus 1 is the line bundle associated with linear hyperplanes using that construction I talked about last time. So you start with a linear hyperplane, associate the line bundle with that, you get O of plus 1. But a linear hyperplane, this is how the cohomology of projective space works. A linear hyperplane in projective space is Poincare dual to this preferred generator of H2. So linear hyperplane lives in the 2n minus 2 homology, and this guy lives in the degree 2 cohomology, so there's a Poincare duality pairing between the two, and both are, the hyperplanes on one side and this class on the other side are just the generators of these respective groups, so they are Poincare dual to each other. And then sort of the same for all integer multiples by dualizing and tensorizing. And that result is actually true in general. So if you have a line bundle that's associated to a hypersurface using this construction from last time, then the Chern class of that line bundle is actually going to be Poincare dual to the homology class of the hypersurface. So if I have D, my analytic hypersurface, then I have this canonical line bundle OM of D. D here. OM of D is the line bundle. And I have this preferred section that cuts out this hypersurface transversely. So it's a canonical section SD. Then it's actually true that C1 of OM of D is Poincare dual to the homology class represented by D. The proof of that is actually not particularly hard. So if you think about it, I mean, this is really just like a soup-up version of this one exercise I put on the first problem sheet. IDD bar log mod f squared is a delta function supported on the zero set of f if f is a holomorphic function from Cn to C. Holomorphic and not identically zero. Or if you want even more simply, that the Green's function of the Laplacian in the complex plane is log r. It's like a delta function at the origin, and now you cross that with n minus 1 complex directions, and that's what you get. So that's what this comes down to. So basically, I mean, the curvature form of this line bundle with respect to any Hermitian metric is basically this up to a smooth part that doesn't actually charge the hypersurface. Like you can decompose, if you want, you can decompose the thing into like its absolutely continuous part and its singular part. Absolutely continuous part doesn't really matter, and the singular part of this measure is supported on the complex hypersurface. Just going to draw a little picture to maybe illustrate a little bit so the geometric meaning of curvature. So positive curvature means that the boundary of the Garrod tube is sort of concave in the outward direction. I mean, the right word is pseudo-concave, but concave isn't the wrong way to think about it. And that sort of means that the zero section, I mean, that's in quotation marks, moves in a holomorphic family, whereas if you have a negative line bundle, then the zero section is kind of rigid and cannot be deformed in a holomorphic way. So the picture I wanted to draw is pretty simple. It should illustrate what I mean. So say you take the origin in Cn plus 1, and you use Cn plus 1 as sitting inside Pn plus 1. So you take the projective completion of affine space. With a picture like this, it's the origin, and sort of you have the hyperplane at infinity, that's a copy of Pn. Then you have lines through the origin. Now, what you can do to this picture is you can blow it up in the origin, meaning you're replacing the origin with a space of directions through the origin, which is another copy of Pn. So you blow up the origin, and what you get is two copies of Pn. So if the lines get separated out by this blowing up process, and so around here, your space looks like OPN of -1. And around here, looks like OPN of +1. Like the zero section embeddings of Pn into the -1 line bundle and the +1 line bundle. So you've got these holomorphic hypersurfaces here. And the one on the right moves in a big family holomorphically, because this is just one particular hyperplane in Pn +1. So we've got all the other hyperplanes in Pn +1. So it's what you call an ample divisor, actually a very ample divisor. It's one that moves in a hypersurface that moves in a large holomorphic family. And for this guy, the opposite is true. It's a complex hypersurface, but it just sits there. It's rigid. It can't be deformed in a holomorphic way. And that's ultimately because, it can be blown down. It came from something downstairs from blowing up. And, the boundary of the Grower tube in this case is just a unit sphere. So if you look from this side, it's outward convex. There's a unit sphere in Cn +1. So if you look from this side, it's outward convex. And if you look at the unit sphere at the boundary of the Grower cube from that side, it's outward concave. You have positive line bundle curvature here, negative line bundle curvature there. So it's a very typical picture. Okay. Over time.
So is
Yeah.
there convexity of concavity of the boundary? Is it convexity of concavity is a contact boundary of a symplectic?
Yes. It means that the CR structure is pseudo-convex, pseudo-concave. I mean, it's what you get if you start with the notion of convexity and then make it invariant under biholomorphisms, for example. It's holomorphically equivalent to a convex set. But in that case, actually, it's really just literally the unit sphere in Cn +1. So that's literally convex in the usual sense. If you look from this side. Okay. Even more homework.